Hello AP Calculus students, this is Related Rates video number 3, and in this video we're going to do a related rates problem involving filling a tank in the shape of a cone, as well as looking at the balloon problem in our notes where we're looking at the rate of change of the volume of the balloon as air is being blown into the balloon. Okay, so we are on page 6 in our notes, and you'll find this problem that I have showed here. We have a situation where water is being poured into a conical tank of height 10 feet and radius 4 at a rate of 10 feet per minute. And we have two questions to answer. Question 1, how fast is the water level rising when it is 5 feet high? And question 2, as time passes, what happens to the rate at which the water level rises? Okay, and it looks like I again forgot my proper units for water being poured in. That is again a volume, so we should say that is 10 cubic feet per minute. Okay, so first thing, we're going to sketch a diagram of our problem. So we have a cone in which water is being dumped into the cone. So we'll get some water there. There's our water. Water's going in, and the rate that our water is entering our cone, dV dt, rate of change of our volume, is 10 cubic feet per minute. Okay, we also know that the entire cone has a height of 10 feet. And we also know that the entire radius of our cone is 4 feet. Okay. So now let's go ahead and write down our givens and our needed information. So our given information, we are given the volume again, so dV dt was 10 cubic feet per minute. And we need, well, for part A, we need to know how fast the water level is rising. So we need dH dt, and at the particular moment in time is when the water is 5 feet high. So that is when H is equal to 5. Okay, so for part A, this is what we're solving for. All right, so the next thing we need to do is we need to come up with an equation that relates our variables. So the equation we'll use, since we're dealing with volume of a cone, we're going to do volume of a cone formula. And that formula is 1/3 pi r squared h. Okay, so now if we look at what we have, volume, okay, that's good. We've got dV dt, so I'm thinking a step ahead when we differentiate. I have r. Okay, so what's r? Well, we know that the final radius is 4 feet. Okay, but here's the problem. The moment in time that is in question, so if you're looking here, we've got this water that's being filled up. The radius of our cone as the water rises is also changing. So here is the r that they are actually asking us for. So we are not sure as to what that value is. We're going to have to calculate that. And h, well, we know that the entire height of our cone was 10, but the moment in time that we care about is when h is equal to 5. Okay, but the r is going to be a problem because, one, we could probably calculate what the value of r is, but we have no idea what the rate of change of r is. Okay, so this is going to be a problem. We're going to have to replace r in terms of h. And this is because we do not know anything about dr dt. Okay, but that's okay because we're going to be able to solve for r in terms of h by setting up a proportion. Okay, so if you're looking at the picture of the cone, we have basically two cones that we can kind of compare to each other. we have this cone right here that is formed by our water. Let's do that in another color so you can see. So here's cone, the small cone, and then you've got the large cone of if the water were filled all the way up to the top. Okay, those are just similar figures, which means we can set up a proportion to write R in terms of H. Okay, so let's write that down. Okay, so if we are comparing the radius to the height, what you want to use are the overall radius and the overall height. We can compare those two. So we know that the overall radius is 4 and the overall height is 10. So now we can just cross multiply and we will get that R is equal to 2/5 of the height. Okay, so now we can take this value for R and we can rewrite our volume equation in terms of just the height. Okay, so we'll do that next. We're going to rewrite the equation. So volume now is going to be equal to 1/3 pi. In place of R, we're putting 2/5 h times, oops, that radius is squared, so 2/5 h squared times the height. And when we simplify that, we get that the volume is equal to, well, we've got to do 2/5 squared times 1/3. So that's going to give us 4/75 pi, and then we have h squared times h, so h cubed. Okay, so now here's our new equation that will relate all of the variables. And now that we have our equation, we can go ahead and differentiate with respect to time. So for our differentiation step, we're going to do the change in volume with respect to time is going to be equal to, well, let's see here. We're going to have 4/25 because we're multiplying by 3 times pi times h, decrease our exponent to 2, times the derivative of h, so times dh dt. Okay, so now we have our derivative equation. Okay, so back to the original question, they wanted us to find out what is dh dt when h is equal to 5. Okay, so go ahead and substitute in the values that you knew. So dv dt, that was 10. That equals 4/25 times pi. Our h, we want the moment that h is equal to 5. And then we are solving for dh dt. Okay, so now solving. Let's see, we've got 5 squared is 25, cancels out the 25 in our denominator. So now we just have 10 is equal to 4 pi times dh dt. And then we can say that dh dt is equal to 10 divided by 4 pi. And that will give you approximately 0.796. And we're looking at a change of height with respect to time, so it's going to be 0.796. Our units were feet per, our unit of time was in minutes. Okay, now a note here, I see this mistake made all the time when you go to divide this. Make sure in your calculator you're putting the parentheses around the 4 pi, so your calculator will divide by the whole 4 pi and not just by 4. Okay. So let's see, that was just part A. So what was part B? Part B said, as time passes, what happens to the rate at which the water level rises? So this is question number 1 that I would like you to think about, and then you're going to come to class tomorrow and talk in small groups. So we're going to answer part B. Think about what you learned from last year and what you know so far. What do you think is the answer to part B? And then we're going to discuss that when we come to class tomorrow. Okay, so the next question we want to look at, we have a volume of a sphere problem. This should be right below the one we just did in your notes. And this problem says air is being pumped into a spherical balloon at a rate of 20 feet per minute. And all my cubes disappeared on my notes. So that's 20 cubic feet per minute. At what rate is the radius changing when the radius is 3? Okay, so our visual model, here's our balloon. Looks a little bit more like a pumpkin. That's a balloon. And we have our radius. So there's radius. And we are putting air into the balloon. So air is going into the balloon, which is a change in volume. And that rate was 20 cubic feet per minute. Okay, so the given information was the dV/dt. And then what do we need? They ask us what is the rate at which the radius is changing. So we need to know what is dr/dt at the moment that the radius is equal to 3. Okay, so we are trying to relate radius with the volume of a sphere. So the equation we're going to use is the volume formula for a sphere. And that formula is volume equals 4/3 pi r cubed. And if we look at our formula, we've got V's and dV/dt, so we're good there. We're going to have that information. And R's and dr/dt's, again, we're okay. So we can go ahead and take a derivative. So when we differentiate, we get the change in volume with respect to time is equal to, when we bring down our 3 times our 4/3, we get 4 pi r, decrease your exponent, times the derivative of r with respect to time. Okay, so we have our derivative equation. And now we can go ahead and evaluate. So dV/dt is what they gave us. That was 20. And that'll equal 4 pi. The value of the radius in question here was we want it when it's exactly 3. And then we are left to solve for dr/dt. And that is radius squared, so 3 squared dr/dt. Okay, so all we have to do is take 20 and then divide by the 4 pi times 3 squared. And what do we get? We get dr/dt is equal to 5 divided by 9 pi. And that as a decimal is approximately 0.177. And our units, since this is radius, so it would be feet per unit of time. And our unit of time in this problem was minutes. Okay, so what I would like you to do on this problem then is write the interpretation. Okay, so tomorrow when you come into class, we will be looking at a variety of problems involving Pythagorean, distance, area, and then volume. And we've got 3 different types of volume problems that we can do at this point. So I will see you in class.